So welcome to this second video on asymptotic analysis or algorithm complexity. And this second video is going to be about analyzing some basic algorithms or basic loops using the Big O notation tool. So let's take a look at this. For example, in this case, we have a for loop and we have for integer count 0, count lower than n, and count plus plus. Now, inside the for loop, there is some sort of sequence of O1 complexity. Now, let's remember very quickly, my O1 complexity is my constant complexity. It's a complexity that doesn't depend on the size of the input. The bigger the input it is, it doesn't matter, it doesn't make any difference, the time is always the same. So in this case, I have some sort of sequence in here that always takes the same amount of time regardless of the size of n. However, whatever time that takes, that is going to happen n times. Why? Because that sequence is inside the for loop that goes from 0 to n. So suppose this takes 1 second, well, that 1 second is going to happen n times. So if n was 10 times, well, this is 10 seconds. But if n is 1,000 times, then that is going to happen in 1,000 seconds, because each one of the operations is constant time. But if I repeat that operation several times, then that time grows. So in this case, we can say that this loop has a complexity O n. And we already saw in my table that O n complexity, which is the linear, is not the worst, but it's not the better either. It's just telling me that within the rank of complexities that I have in the big O category, O n is somewhere in the middle. Let's take a look at another loop analysis. So in this example, I have a while loop. So I have a variable count that is equals to 1, and I have a while loop that goes that is going to repeat itself until count, as long as count is lower than n, and n could be any value. Now, what is important here is that we need to take a look at what is inside the while loop. So inside the while loop, I have some sequence of O1 step. Again, whatever thing I have inside is always going to take the same amount of time. So how many times is this going to happen? Well, that's where things are going to be interesting, because it really doesn't happen n times, because count is increasing faster than in a linear way. So count is multiplying by 2 every time. So when count starts at 1, well, in the first iteration count becomes 2. But in the third iteration, counts become 4, and in the next one becomes 8, and in the next one becomes 16. So as you can see, the growth of count is faster than a linear growth. So it's a little bit bigger. So that means that this while loop is not going to happen as many times as n. So that algorithm is known, or that sort of algorithm is known of category log n. So let's go back to the table. We can see it's not as good as a constant algorithm, but it's not as bad as a linear algorithm, because it's growing not as fast, or it's not going to happen as much as if it was linear. It's going to happen a little bit less, but not as less as constant. Good. So another example would be, for example, having double for loop. I can have a for loop inside a second for loop, which is what we have in the screen. So we have one count that goes from 0 to n, and I have another count that goes from 0 to n. So, and inside the second loop, you have something that is O1 category. There's something that takes always the same amount of time. So if I have something that takes the same amount of time inside a for loop, well, I already know that that is going to be complexity O(n), because the bigger n is, the longer the whole thing is going to take to run. But then if I put that inside another for loop, for each iteration of the outer loop, for each iteration of the outer loop, I'm going to have a full iteration of the inner loop. So these two complexities are going to multiply to each other. So this is complexity n, this is complexity n, so the overall efficiency is going to be called O n squared. Just going back to the table, I can see the n squared is somewhere down here. So if I have something that is n squared, it's not as good as something n or log n or even n log n. Now, suppose you have nested methods. So you have a method that calls another method. So that is also a possibility. And what you have to do in that case is that you need to make sure that you do the analysis of each one of the methods individually. And then you have to multiply or add up according to the case. So you really need to have a look at that carefully. Okay. So these three examples that I'm explaining here, they're called, they're a way of theoretical analysis. And that's exactly the kind of things that I'm going to expect you to start doing on your own. I have posted upon Moodle another example of theoretical analysis, and I will keep giving you some exercises so you can do the theoretical analysis of several algorithms, so you can tell me in what category they fall under. So it is a high-level description of the algorithm instead of the implementation, so I don't need to run the code. Only taking a look at the code, I can know whether the algorithm is good or bad. It characterizes running time as a function of the input size. So if I have something that is depending on the input, then I can roughly know if it's going to take longer or shorter. It takes into account all possible inputs because it's a function of input. So it's a good way of doing the analysis, and allows us to evaluate the speed of an algorithm independent of the hardware of the software environment. Now, that's something that we're going to talk about in a second in the third video, but if you think about it, if you have a stronger computer, whatever algorithm is going to run faster. Now, so one of the good things of the theoretical algorithm is that regardless of the hardware, I can know in absolute terms whether the algorithm is good or not. Okay, so we'll leave this video until here. As I said, I'm going to be posting more some other material on Moodle for you to analyze some algorithms in there. And then we'll have a look at the third video, which is going to be a practical analysis using Java implementation. So that's going to be the next one. Thank you very much for watching, and I'll see you in the next video.